Today we need to go over two more gas laws. We're going to go over Avogadro's law and the combined gas law. So if you could get your notes packet out. Now, I hope you recognize the name Avogadro. You should. He was the highly attractive mole guy. Avogadro's number, 6.02 times 10 to the 23. But he also, the whole mole came about because Avogadro did research about gases, and he found that if you have an equal volume of gas, so like if I have 1 liter of carbon dioxide, 1 liter of oxygen, they're going to contain the same number of moles. Now, this is only true when temperature and pressure are constant, so they don't change. And this is true for any gas. So whether it's carbon dioxide, oxygen, carbon monoxide, whatever poisonous gases there are, if two gases are at the same temperature and pressure and you have the same volume, both of them, so same amount of liters, they'll have the same amount of moles. And so this is our equation. Volume over moles will equal the new volume over moles. And moles is actually represented by an N. It's not an M because M is mass. So moles gets an N, close enough to it. And then they are at a direct relationship. And so you probably want to draw this graph in there as well. So as the number of moles increases, as you go from like 1 mole to 2 moles of a gas, the volume will also increase, which would make sense. The more gas particles you have, the more space they take up. And we've got one example problem to do with Avogadro's law. So again, I'll write the equation. It's V1 over N1 equals V2 over N2. Okay, so we have 14.3 liters of oxygen, and it has 1.2 moles of gas in it. So my initial volume, my V1, is 14.3 liters, and it's oxygen, which is O2. My N1, my initial moles, is 1.2 moles of oxygen. And I keep pressure and temperature constant, so that means I can use Avogadro's law. And I decrease the volume to 10.7 liters. So my volume has gone down. V2 equals 10.7 liters. What is the new amount of moles of gas? So I'm looking for my new moles, N2. And then the second question, how many grams of oxygen is this? Well, we'll get to that in a second. So you would list your variables, see that, okay, there's only V and N. I'm going to use Avogadro's law. And then both of my volumes are in liters. So they don't have to be in liters, but if V1 is milliliters and V2 was, liters, you would have to change one of them so that volume are in the same unit. So make sure your volumes are in the same unit, and N is always moles, not grams, it's moles. And so our volumes are in the same unit, N is moles. We can plug this into the equation. So 14.3 divided by 1.2 equals 10.7 divided by N2. To solve this, you can cross multiply. So I'm going to multiply these together and then those together. And I end up with 14.3 times N2 equals whatever 1.2 times 10.7 is. And when I multiply those, that is 12.84. Now remember, you're cross multiplying. So this 14.3 is being multiplied by N2. So to get N2 alone, which is what I'm trying to solve for, I have to divide each side by 14.3. So now it cancels out over here. And whatever you do to the left side of the equation, you do to the right side of the equation. So N2 equals whatever that is. And that is 0.8979 yada yada moles. If I look at significant figures, there are two significant figures in this number. So this one, I would take, it would be fine to say 0.89 moles of O2 or 0.90. That's probably the more correct answer because it's 8, 9, 7, etc. But both are fine. So that answers the first part of the question. Oops, you can't see that. There we go. The second part of the question was, how many grams of oxygen is this? I told you mole conversions were never going away, and I wasn't kidding. So we know now that the new amount of moles of gas is 0.90 moles, and we need to change that to grams. So 0.90 moles of O2. To go from moles to grams, we need to set up a little conversion. 1 mole of oxygen at the bottom. Okay. Sorry, I'm recording this video actually during finals week on Christmas, so announcements. So we're changing this to grams. Now remember, this is O2, and so the molar mass of oxygen is whatever O is, there's 2. So 15.999 times 2. When you multiply that, that is 31.998. So that's how many grams there are in 1 mole of oxygen. And so it might help if you, especially if I'm going to ask for grams, if you write what the substance is, make sure if it's a Hofbrinkel, hydrogen, oxygen, fluorine, etc., that it is a 2. And then let's solve that. And that is, running out of room, 29 grams of oxygen. Now you should stop and do a common sense check. The volume was 14.3 and it had 1.2 moles of gas. The volume decreased. My moles of gas decreased. That it makes sense, and that's what our equation tells us, that volume and moles are in a direct relationship. If you ever get a number where volume is decreasing but moles go up, you did something wrong. So always double check that. And that is Avogadro's law. Now, the combined gas law, guess what that is? All of the gas laws combined. And this is the equation. So you would use, I'll let you write this down for a second, but this gas law is all of them put together: pressure, volume, moles, temperature. And it looks really big and really scary. The hardest part of the combined gas law is honestly listing your variables and making sure you get everything in the right spot. And so you would use the combined gas law when you have multiple variables changing. So let's say pressure changes, volume changes, temperature changes. That's when you would use this equation. And you'll be able to figure out when to use the combined gas law and when to use your other formulas if you simply list your variables like I've been doing, right? P1 equals, P2 equals. And anytime it's got all of these numbers, it's the combined gas law. Now make sure that temperature has to be in Kelvin. It can't be in temperature. N is moles, and the unit for pressure and volume don't matter as long as the unit for P1 is the same unit as P2, and so forth. Okay. And we have 2 examples of these that we're going to do together. Okay. So the combined gas law again, all of them together, P1 times V1 over N1 times T1 equals P2, V2, N2 times T2. Okay. So a 2-liter container with 1.3 moles of nitrogen gas is filled to a pressure of 104.3 kPa at 285 Kelvin. Let's list all of that down. So I have my initial volume. My V1 is 2.0 liters. My N1 is 1.3 moles, and it's nitrogen, so that is N2. I'm going to write that down just in case I need to remember that later. My pressure, so my P1 is 104.3 kPa and my T1 is 285 Kelvin. The temperature was lowered to 271 Kelvin. So that's my temperature too. 271 Kelvin. The pressure also changed. It's now 96.5 kPa. So my P2, 96.5 kPa. And my V2, my new volume, is 152 milliliters. What is the new amount of moles of gas? So I'm looking for my new moles, my N2. If you just go through the problem, list your variables, you would look at this and say, oh my god, I've got all of these letters. That's the combined gas law. Now, let's double check, and you might want to go through like with a different color or something. My V1 is in liters, my V2 is in milliliters. Not the same unit, you need to change one of them. It doesn't matter which one you change. I don't like using milliliters. I prefer to use liters because they're smaller numbers, so I'm going to change that one. And so to go from milliliters to liters, you divide by 1,000. And that is 0.152 liters. Okay, they're in the same unit. N1 is moles, I'm looking for N2. P1 is in kPa, P2 is kPa. That's good. Both my temperatures are in Kelvin, what they're supposed to be. So all of my units look good now. I can plug this into the equation. And then make sure you put things in the right spot. So it is P1 times V1. My P1, 104.3, times my V1, which is 2.0, over my N1, 1.3 moles, times my T1, 285, equals P2, 96.5 kPa, times my V2, 0.152 liters, over my N2, we don't know, times my T2, 271. Now, there are a lot of ways mathematically you can solve this. It doesn't really matter the order, if you do it differently than I do, as long as you'll get the same answer, assuming you do your algebra correct. You can cross multiply, and so I'm going to do that, but make sure, especially because there are so many letters, you don't forget to multiply everything. So on all of these, I'm going to type in the calculator, 1.3 times 285 times 96.5 times 0.152. And that equals, multiply all of those together. And that will equal, we're going to cross multiply this side together. So 104.3 times 2 times 271 times N2. Running out of space. But just make sure you don't forget everything. So I'm going to solve my left side of the equation first. 1.3 times 285 times 96.5 times 1.52. Multiply those all together, and that is 543. And that equals, now multiply this out. 104.3 times 2 times 271. That is 56530.6, and it is times N2. So to solve for N2, we need to divide each side by this number to get N2 alone, or isolated. That cancels out, and let me divide this. Divide that, now I have N2 equals 0.096 moles. And that would be my final answer. So, formulas seem scary. It's not really scary. It's just a lot of variables to keep track of. And then making sure you do your algebra correct. we have one more we're going to do together to make sure you're okay, and then you're going to jump into your Avogadros and combined gas law problems. Okay. So this one. Containers filled with a pressure of 2 atm and a temperature of negative 73 Celsius. And then the container is then altered. So it's changed. The resulting pressure is 567 kPa. The new temperature is 405 Kelvin. The final volume is 105. Find the initial volume of the container. First thing, list your variables. So it originally had a pressure of 2 atm and a temperature of negative 73 Celsius. I know I need to change that to Kelvin, so let's do that immediately. Plus 273, that's 200 Kelvin. Okay, and then it asked, find the initial volume. So V1 is our unknown. Then the container was altered, so it's changed. The new pressure, my P2 is 567 kPa. My T2 is 450 Kelvin. And my V2 is 10.5. And it didn't say a unit. That is a typo. I'm going to say it's liters for our sake. Sorry. Okay, so I would look at this PTVs. There is the only gas law that has 3 variables in it is combined. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, you'll find this with some combined gas law problems. We have P1, we have V1, we have T1. We have P2, we have V2, we have T2. We don't have anything about N. If you are missing N1 and N2, you can just pretend like N is not a part of the equation. And that goes for other variables too. If I don't mention, like let's say I didn't mention a P1 or a P2, just forget about it. You can assume in this case that the moles of gas isn't changing, which if it's not mentioned, assume it's not changing. And if it's not changing, then it's not going to change the numbers at all. And so if I don't mention moles, just forget about it, that it's a part of the equation, like I did. So this one's just going to be pressure times volume over temperature. Now let's check our units. P1 is in atm, P2 is in kPa. It is personal preference. I like to use atm. kPa numbers are bigger, so I don't like to use that. And I'm going to change that one then. But if you wanted to switch atm to kPa, go right ahead. The conversion is 101.3 kPa, or in 1 atm. Oops. And so that is 5.597 atm. My temperatures are both in Kelvin, and I'm looking for my new V1. All my variables look good. Let's plug this into the equation. 2 times, I don't know what V1 is, over my T1, 200, equals pressure 2, 5.597, times my volume 2, 10.5, over my temperature 2, 450. And again, you can solve this algebraically however you want. I'm going to cross multiply. So multiply those, that's 2 times 450 times V1 equals, cross multiply the other side, 200 times 5.597 times 10.5. 450 times 2 is 900 times V1 equals and I cross multiply these, that number is 11753.7. And then to solve for V1, you need to isolate your variable, divide each side by 900. And V1 equals 13.06 liters. Sig figs, 13 liters. And that is the combined gas law. Seems scary, not terrible. Today, you're going to work on your Avogadros and your combined gas law problems. Should be page 7 and page 8. Good luck.